Artemis, the sister of Apollo. She will soon be returning humans to the moon. The decades of development are nearly complete. New hardware, new ways of making the journey, and new goals have been set. This time, the United States will not be going it alone. This time, it's an international effort. The first major test will be Artemis 1, an uncrewed journey to the moon and beyond, a final hardware shakedown for manned flights.
Nowadays, astronauts, engineers, and scientists are very excited to go to the moon because it's pure exploration. It's discovering terra incognita. We would go to regions that were never been, well, explored by a human, neither robotically nor in person. The moon is really our eighth continent, and it's there to be discovered. Last time humans have been there was in the 60s and 70s, and they covered, well, 12 people covered 6 landing sites, and imagine that in an area that's so huge. It really doesn't give us a lot of knowledge about the moon itself.
2, 1.
This lunar spacecraft comprises ESA's ESM and NASA's Orion crew capsule. It will be used for an uncrewed certification flight, performing a 6-day orbit around the moon.
We returned to the moon for various reasons, different technologies, and it is a big achievement, I believe.
All over in Europe, we have companies in 10 countries helping to put this ESM together, which is quite significant. And actually, there are hundreds and thousands of people working within Airbus, but also in our partner companies, to make this endeavor a successful mission.
Monitoring of the performance of the ESA segment will be conducted here at ESTEC in the Netherlands.
These folks here are specifically taking care of the European Service Module, which provides the human capsule part of that with all of its power and life support. So this team here is really taking care of the crew that will be going to the moon and beyond.
So there are mainly 2 types of support. That's basically 2 types of situation. Nominal situation, everything goes fine. Here we are actively supporting, actively monitoring the spacecraft, looking at the trend of the parameters to try to predict as much as we can if something is, if a failure is building up or if everything is nominal. And again, anticipation is the key, meaning that you have to know your mission and you have to know what's coming up, what's coming next, for instance, if it's, and then things you cannot predict, and that's why we are training with failures in the simulations. These are failures. And to failures, how we react, how we talk on the voice loops, how we communicate throughout the position between the various subsystems to quickly identify what is the failures, to investigate it, to understand the root cause, and also any likely impact onto the other subsystems, on the system, and also on the mission.
It's human space flight, and you're always going to have anomalies. We don't say a problem. A problem is indicative of something you don't know that, but anomalies come from engineering. You can find them, solve them, and continue on. And that's what the teams have been working through recently through the wet dress rehearsals. There was 4 dress rehearsals to make sure everything's absolutely right.
any way you can do like this.
Yeah, you can.
If you click shift.
Today's simulation is what they call an inspection simulation. So the idea is during a launch, they will do a systematic inspection of the entire spacecraft. The European Service Module sits on top of the NASA SLS rocket. So basically, on a pre-launch check, they'll just really systematically look at every piece of those vehicles, trying to identify any potential anomalies or such before they fly.
The surface of the moon has about the same area as Africa, and we only visited the moon 6 times in the 1960s and 1970s. So if you think about landing in 6 different spots in Africa, you quickly realize that there's so much more left to learn and understand about how the moon formed and how it's evolved over the last 4.5 billion years.
Before NASA's Artemis astronauts go to the moon, a small spacecraft called Capstone is leading the way. This small spacecraft will test a unique lunar orbit that has never been flown before. This orbit will be home for NASA's Gateway elements.
Behind me is a mock-up of the Habitat and Logistics Outpost, or as we call it, the HALO module. The HALO module and the power and propulsion element will be delivered to lunar orbit to make up the first components of NASA's Gateway. The Gateway is going to be crew-tended, where crews will visit the Gateway for a period of a few weeks or a few months. HALO and the PPE are just the first components of the Gateway, with plenty of room for future growth. Northrop Grumman has been delivering cargo to the International Space Station using the Cygnus spacecraft since 2013. That's 15 missions and counting. We are now using that Cygnus experience and our lessons learned in the design of the HALO module.
With the power and HALO modules in place, the Gateway will be built up over several launches. The IHAB module will be delivered by the first manned Orion mission. A logistics module with the Canadian robotic arm will be next. The lunar landing system, then Artemis 3, will deliver the refueling infrastructure and telecommunications module before proceeding on to a landing at the lunar southern pole. Before any descent attempt, a crucial component for Artemis is location of a landing site. Unlike the Apollo missions that landed along the relatively flat equatorial regions, Artemis will be landing at the southern pole of the moon, a far more challenging landing scenario. Six landing regions have been identified, close to the permanently shadowed regions where water may be found. However, further exploration of these sites is required to pinpoint the most ideal landing location. This will require the services of robots. NASA is sending Viper to scout the terrain.
Viper is a rover of many firsts. The first NASA rover to map water resources, and it's the first rover to wear a headlight.
Viper will be one of many robots descending on the lunar pole in search of water. Testing these robots is well underway in terrain most lunar-like.
Traditionally, rovers are operated from the Earth. With the lunar gateway being put in place around the moon, there's the possibility of controlling them directly with much smaller time delay. And this opens up for new possibilities for things that you simply cannot do or is much more difficult to do from the Earth. So now we're here in Sicily. We're repeating our experiments on the slopes of Mount Etna. The astronaut is not on the International Space Station. He's controlling from a hotel room here. We have our European Space Operations Center in Germany, in Darmstadt, who are directly overseeing and running the operations. And in the role play, they are pretending to be on the moon, and it's very realistic because the slopes of Mount Etna is a wonderful lunar analog. It looks exactly like the moon. There's beautiful craters, there's rocks, it's grey. So we have the European Space Operations Center able to really immerse themselves in the role play, feel like they are planning traverses and exploring regions of interest on the moon in close discussion with the scientists who also get this full immersion where they see a realistic lunar-like geology, so they can have a real discussion. They need to then communicate this to the European Space Operations Center, who has to then make decisions about how they are going to execute operations, whether they make use of the astronaut for direct teleoperation with a short time delay, or whether they make use of their own tools for planning longer traverses and not wasting astronaut time on this. So this is the type of trade-offs and the sort of things that we want to learn how to do for real when we go to the moon, by playing essentially the scenario, playing the game here on Mount Etna. The astronaut is doing the same as he did on the International Space Station in 2019. So he has a control station which allows him to fully teleoperate the rover. What I mean by that is that he can drive it, he can control the arms with the direct feedback. So we have a very immersive control station which allows him to feel a bit like he's on the surface. The robot is his avatar on the surface. It's designed so that he can touch things with the robotic arm and feel what the robotic arm feels. It's designed so that he can decide whether he wants to drive with the joystick, or he can plan his traverses and automatically do it. He can choose whether he wants to manually pick up rocks, whether he can do it automatically. And we really want to learn from his experience which of these tools he is using, which of these tools he is finding useful in different situations, and how his interactions are happening with the science team, how easy it is to communicate which samples to pick up, how the interactions are going with the European Space Operations Center, when they think it's better that he uses his tools to do it, or when it's better that they do it, how the handovers are working. All of these things is what we're trying to learn here. It's a very complex experiment because it has a lot of stakeholders, a lot of partners, because there's a lot of different objectives. We are trying to validate technologies that have not really been used extensively in space. We have this device we used in 2019. It's the first time something like at this level of complexity has been used to control robots from the space station. We have the whole operational scenario, which involves a lot of parties, this game, which is we're trying to learn a lot from. So this complexity makes it a very challenging experiment, but that way we learn a lot.
We are here at Mount Etna in the frame of the Artemis campaign, and this campaign is organized by the German Aerospace Center. So there are multiple robots from the German Aerospace Center, via guests, our robot from ESA, and also other research institutes are actually practicing with their robots how it is on a real scenario. So here on Mount Etna, it is very close to what we expect on the moon in sense of soil conditions and harsh environment, dusty, rocky slopes and loose sand. Our robot is controlled today by an astronaut. For this purpose we invited Thomas Reiter. And for us it's important that's an astronaut because in these scenarios we want to practice what happens in reality. So there would be an astronaut sitting in the spacecraft and controlling a robot on the surface of a planet. And in the past we have done this with the ISS. So we had Luca Parmitano in 2019 with Analog 1, controlling our robot in a hangar in Falkenberg. And here, of course, we are on Mount Etna, moon-like scenario, but it's very difficult to have an astronaut on the ISS controlling a robot here on the mountain, to have all the logistics and everything set up at the same time. But to have a fair comparison, we indeed have Thomas Reiter in the hotel room in Catania, controlling a robot here in a realistic scenario.
Yeah, today was a very special scenario because we tested the cooperation between a ground control, people who are sitting in a control room somewhere on Earth, and the crew that is orbiting around the moon in the lunar gateway. And this specific cooperation turned out to be extremely fruitful. In earlier times, it was always thought that there is either a purely robotic operation, which is exclusively controlled from control centers on the Earth, and the crew doing something in situ, being really on the surface of the moon. And I think what we learn here is that this kind of collaboration that you are doing from ground control on the Earth, a crew that is on board a space station that is orbiting the moon, and a rover that is on the surface, can be extremely efficient and much more efficient than actually if either one does it alone.
Well, it's certainly less dangerous to send a rover to the surface than to send an astronaut. It's also cheaper. It's also possible to not take up so much of their time. You know, astronaut time is extremely valuable, so you can send a rover to the surface. You can let the ground team do all their planning, let them do all the longer traverses, and you get the astronaut involved when it's necessary for maybe the more complex task or the things where he really direct teleoperation, direct control of the robot is more helpful.
Our rover is built by the lab and it's a demonstration rover. So we want indeed to figure out what features do we need in a future space mission. So of course if you control a rover, you need for awareness video cameras for the simple ones. But of course to go somewhere you need a locomotion platform, and it needs to be fitted for this loose soil underground, and to manipulate things, for example pick up rocks or maybe later maintenance of infrastructure, you need robotic arms. And so our robot was constructed with this purpose in mind, to have it controlled by an astronaut with force feedback to perform this kind of tasks. But of course we are also looking in the future, so direct teleoperation is good, but of course we also want to enhance our system by more and more autonomous features. And so there my team developed, for example, automated rock detection, so that the astronaut doesn't need to grasp the rock manually, but indeed that the machine learning algorithm detects a rock, controls the robot to grasp it automatically. And this way we want to step by step increase the capabilities to automated driving, automatic obstacle detection, rock detection, to come actually from a remote operated system to a more autonomous system. today we try to achieve a full control and a full scenario of our robot. So in the past experiments, we went always step by step. So we had a force feedback device on the station, we had a robot in a controlled environment, and indeed this is one of the first times we put out the robot in a really harsh environment here on Mount Etna. So it's moon-like, we have a complex scenario with the operations center in the background, the astronaut with time delay in the control center, and indeed a task that has been prepared by the team in Darmstadt that was not known to the scientists and to the astronaut beforehand. So here we really try to get as close as possible to real scenarios with surprises in a hard environment. And if we master this, we are really confident that these technologies can be developed further to make it space grade, to indeed be part of the next moon mission.
In our scenario, which is based on a notional mission based on the European Large Logistic Lander, the astronaut, in collaboration with the European Space Operations Center, will be collecting the samples, bringing them back to the lander, and then they will be brought back to the gateway or directly to Earth for analysis by the scientists.
Autonomous robotics will be used not just on the moon, but farther afield. Plans are underway with the Mars Sample Return mission. Landers and launchers are being developed for this mission that will see an autonomous robot, or even perhaps helicopters, that will land on Mars and pick up the samples collected by the Mars rover. Once brought back to the lander, they will be loaded onto a launcher, returned to orbit, collected by the orbiting vehicle, and carried back to Earth via a small re-entry vehicle holding the precious cargo. We have looked up to the stars and galaxies in awe and wonder for millennia, trying to understand our place in the universe. Current technology is enabling us to see further and farther back in time with much more detail than ever. The next generation of orbiting telescopes is soon to enter service. Who knows what giant leap they will make in our understanding of the universe. Since its launch in 2013, ESA's Gaia Observatory has been constantly mapping our galaxy, creating the most accurate and complete multi-dimensional map of the Milky Way. This latest observational dataset has been released and contains even more and improved information about almost 2 billion stars, solar system objects and extragalactic sources. Our Sun travels at 240 kilometers per second around the galactic center and will take 220 million years to complete one orbit. The Gaia dataset includes stellar positions, stars' distances, and motions across the sky, plus color information, and most significantly, the radial velocities for 33 million stars within the Milky Way. This allows astronomers to create the most accurate and complete multi-dimensional map of our astronomical neighborhood. Another novelty in this dataset is the largest catalogue yet of binary stars in the Milky Way, which is crucial to understand stellar evolution. At the Observatoire de Paris in Meudon, Paris, France, scientists form part of the Data Processing and Analysis Consortium, some 400 scientists from 20 countries who are responsible for the processing of Gaia's data with the final objective of producing the Gaia catalogue.
So Gaia is extremely important for all fields of astronomy. The Gaia catalogues, that results contain a huge amount of information that will provide the material for the work of astronomers in around the world and for many, many years.
With each new release, the observed stars, solar system objects and extragalactic objects increase, and many more details are added to what is already the most detailed overview of our galaxy.
So Gaia is an incredible satellite which looks at the stars, which measure 1.8 billion stars, but obviously it goes from what is nearby, asteroids, up to very distant quasars. For these 1.8 billion stars, it's able to find their distance, their astrophysical parameters, their ID card in some sense. Up to now, Gaia had given already a lot of information about stars, but now it's going from astrometry, the position, motion of the stars, up to astrophysics, knowing the characteristics, the astrophysical parameters for nearly 500 million stars. It is able also to find a lot of variable stars, to classify them. It's able, of course, also to see what is variable in terms of position, and so it helps to find binary stars which move on the sky or on the spectrograph.
And this time we provide new measurements such as star brightness in the RVS spectral range, rotational velocities, atmospheric parameters, chemical composition, and the RVS spectra also provide information on the abundance of the interstellar material that is present between stars.
So Gaia is observing with astrometric instrument which measure the position of the objects, and from this position it gets the motion of the object with time on the sky. That's astrometry. Then Gaia measures also the light of the object, measure spectrophotometry for the object, and from this it can infer the color of the object, but also you can derive from that all the astrophysical parameters that you can get, like temperature, effective temperature, gravity, and so on. You can also infer what is the extension of light in the distance where it comes from the star to us. So the third instrument now is a spectrograph, which is able to see the spectrum of the star. And so when you see the lines of the spectrum, you see at which speed the object is going towards us or and the other way around. Or when it's moving periodically, then you can detect through the motion of this radial velocity. That's the three main instruments of Gaia.
Even older than Gaia is the venerable Hubble Space Telescope. It too continues to contribute to the science of cosmology.
To my mind, the most important discovery from Hubble is the discovery of dark energy. There have been a lot of interesting discoveries, certainly. Certainly the fact that there are billions and billions of galaxies that we had no idea there were that many. The work that we were doing on exoplanets with Hubble has been interesting. I mean, Hubble has carried such a wide variety of results that it's hard to pick a single one, but I do feel the dark energy is the outstanding discovery. And what that means is simply that space, we always thought that space would contract because gravity would pull it together. We knew it was expanding, but we thought the expansion would slow down. Well, instead, the expansion's speeding up. And that is a very exciting thing to me.
Because the Hubble Space Telescope is operating so well and is so scientifically effective right now, scientists are using Hubble to investigate some of the deepest mysteries of the universe. One mystery is dark energy. That's the name just kind of plastered on this phenomenon that Hubble and other telescopes together, we found that the universe expansion has been accelerating for the last few billion years. Well, what is causing that? We don't know. It's something about a repulsive force that we may not fully understand or new physics that we don't fully understand. But Hubble was used along in complement with some telescopes on the ground to determine that the expansion of the universe is in fact accelerating by something we're now calling dark energy. And without Hubble, we would have not been able to make this detection, which is now a Nobel Prize-winning discovery.
This explains why the universe appears to be accelerating now when it used to be slowing down because of gravity. So now the question is, well, is this a simple story or is it complicated? Is there more than one kind of dark energy? Has the dark energy itself changed over time?
So Hubble is now being used to refine even further that expansion rate of the universe in our current epoch, and trying to compare that to what might be predicted from looking at other measurements of the universe with other telescopes. Right now we're finding a discrepancy between what we might have expected and what we're actually measuring. So that's one realm where Hubble is really at the cutting edge of helping us understand, or at least open up, new mysteries of the universe.
Astronomers are still puzzling over dark matter and how it behaves. They have found small, dense concentrations of dark matter that bend and magnify light much more strongly than expected. Dark matter makes up the bulk of a galaxy. The gravitational influence of dark matter is thought to tie the galaxies together in massive clusters. There is so much regular matter and dark matter concentrated in these clusters that their gravity magnifies and warps light from distant background objects. By studying how the light distorts the background galaxies, though, this gravitational lensing can help map where the dark matter is in galaxy clusters. Images of lensing galaxy clusters are filled with the smeared images of remote background galaxies. The higher the concentration of dark matter, the more dramatic its light-bending power is. Smaller clumps of dark matter associated with individual galaxies in the galaxy cluster create more distortions. In some sense, the galaxy cluster acts as a large lens that has many smaller lenses embedded inside. But strangely, astronomers found that 3 galaxy clusters used in their study had concentrations of dark matter that are so massive that the lensing effects they produce are 10 times stronger than originally expected. Soon to be launched, ESA's Euclid mission aims to investigate this dark matter, dark energy, and the expanding universe in even greater detail. Euclid will image billions of galaxies with unprecedented accuracy out to a distance of 10 billion light-years. These measurements will enable astronomers to improve their understanding of the expansion of the universe and the growth rate of cosmic structures.
Euclid is a cosmology mission. It will study and try to better understand the geometry and the nature of the dark matter and dark energy, which is the peculiarity of Euclid. It's a telescope that will scan the sky with an accuracy that is unprecedented. So this is really something that no other spacecraft did before. This will allow to get additional information and to better understand the story and for the expansion of the universe and the growth on the cosmic structure.
Euclid carries a 3-mirror anastigmat design. The primary mirror is 1.2 meters in diameter. This type of design allows for a greater field of view, covering the visible wavelengths and simultaneously near-infrared spectroscopy and photometry.
It was a very important milestone because it's somehow the starting point of a new phase of the project, because so far the 2 parts that you can see, the upper part that is the payload module and the lower part that is the service module, have been developed and tested separately. So today with the mating we start a following phase, the next phase, with both the 2 main constituents of the Euclid spacecraft are together.
Indeed, this is a completely new design with a lot of challenges involved with this mission. And we have put together a team of about 120 companies in Europe, which are working together in good synergy for several years. And we are very proud of the results achieved today.
The mission is designed for a 6-year lifespan. However, an extension of a further 5 years is contemplated, dependent on the spacecraft's onboard resources.
With the mating today of the telescope with the service module, we achieve a major milestone in the integration of the flight satellite. It has been a long journey because the 2 elements have been developed independently for several years, and now for the first time they are mated together, and this makes us very proud of the achievement.
So the telescope was already delivered here in October last year and was put in the clean room on the fixture, ready to be mated. In the meantime, we finished the work to be done on the remaining part of the satellite, which is here. And today we released the telescope from that foundation and we move it to the SVM by crane. It is a very dedicated operation because the tolerances or the budget we have for the mechanical stresses is very small. So it's a very fragile telescope because it needs to be light. So it's quite fragile. So for this operation, there was a tight allocation for the stresses. And the stresses they measured at every step on the feet which support the satellite on 6 points.
Next step after this mating will be the integration of the solar array sun shield, which will happen around May this year. And at that point, the satellite will be in full flight configuration. And at that point, we will go to Cannes to conduct the environmental test campaign for about 6 months. The objective is to have the satellite completely integrated and validated at the beginning of next year.
After the mating, the next step will be the finalization of all the connection, electrical testing. Then in front of the telescope will be installed the sun shield and the solar array, and after that, the eye gain antenna. Then the test campaign will start in Cannes. The full spacecraft will be tested in environmental condition, and at the end it will be ready to be shipped to Kourou for the launch campaign.
Launching around the same time as Euclid is NASA's SPHERE-X mission. It will survey hundreds of millions of galaxies near and far, some so distant their light has taken 10 billion years to reach Earth. Also, it will search for water and organic molecules within the Milky Way.
SPHERE-X is NASA's latest Explorer mission in astrophysics. It's a small telescope, but it has this unique and powerful capability of doing spectroscopy everywhere.
We are going to survey the entire celestial sphere and collect a data set that will help us answer 3 fundamental science questions.
It's going to tell us about the origin of the universe, the birth and formation history of galaxies, and the abundance of essential molecules such as water in the early stages of star and planet formation.
The great thing about SPHERE-X is not only will we view the entire sky 4 times, but we will see it in nearly 100 near-infrared colors. And that's really never been done before.
According to our current understanding of the universe, we think that in the very earliest times, and I'm talking here a fraction of a second, much less than a nanosecond, the universe appeared to have gone through an accelerating expansion called inflation. And this is really a profound idea, and we're very interested to test it. And so one way to do this is to look at how matter is distributed over the universe. We want to map hundreds of millions of galaxies in 3 dimensions. What SPHERE-X does, in addition to mapping out all these galaxies, is we cover the whole sky. So we can measure these galaxies over the largest part of the range we can see, which is the entire sky. And we want to cover the full range of distances from today to as far back as we can see.
We know there are about 100 billion galaxies in the universe, maybe more. But we still don't have a good understanding how these galaxies came to be. Did they all form at the same time? Did they change in size and luminosity or brightness over time? So the intent with SPHERE-X is for us to figure out the formation history of galaxies, where do they exactly form, and how do they grow over cosmic time. And that information is crucial for us because that'll allow us to separate various theories we have right now on the formation and growth of galaxies.
SPHERE-X will also identify targets for more detailed study by NASA's James Webb Space Telescope and the future Nancy Grace Roman Space Telescope. The Nancy Grace Roman Space Telescope is set to launch atop a SpaceX Falcon Heavy within the next few years. It will capture images unlike any satellite before it. The Roman Space Telescope will have the same image resolution as Hubble, but with 30 years of technological advancement, will cover an area 100 times larger. Roman will also view the sky in carefully selected wavelengths of infrared light. This will allow scientists to see through the obscuring dust to reveal hidden stars and watch the growth of galaxies over the last 10 billion years. Because Roman will be seeing further back in time, accurate measurement of distant stars is critical. A small galaxy close in looks similar to a large galaxy farther out. One method used by astronomers to gauge distances is something called a standard candle. A standard candle is a type of stellar object or event that emits a specific known amount of light. This works because light sources appeared predictably dimmer the farther away they are. So, for further distances, astronomers have to rely on the brightest of stars or events, in particular exploding stars called supernovae. There are a few different kinds of supernovae, but the best for standard candles are type 1a. These supernovae involve a white dwarf, the leftover core of a dead star, and one other star in a binary system. The white dwarf accumulates mass from its partner and eventually explodes, giving off a set amount of light. These beacons then allow scientists to accurately predict their distances. Roman will also use its broad view to search for planets around other stars in our galaxy. It will be fitted with a coronagraph which reduces the light coming directly from the star to separate it from the light reflected by the planet. The Roman Space Telescope's coronagraph doesn't block the star's light. It uses a combination of disks with complex patterns and light-blocking stops to create destructive interference with the star's light, effectively making it disappear while allowing the light from planets to pass through. A complicating factor is that the light picks up small distortions as it reflects off the telescope's series of mirrors, and these distortions can reduce the effectiveness of the destructive interference. Collecting more light increases the image signal, but the planets are still hidden under blobs of leftover distorted starlight. To remove these blobs, the coronagraph has special deformable mirrors that can change shape by using hundreds of tiny pistons. This corrects distortions in the light beam. As the mirrors deform, the blobs of light slowly disappear, revealing brighter planets. Advanced software processes this data, further improving the contrast and clarity of the image. This processing makes objects more than 1 billion times fainter than the star visible. As a result, the Roman Space Telescope will provide the first look at individual planets in star systems that might be similar to our own. The Nancy Grace Roman Space Telescope will also look for the fingerprint of dark matter and dark energy in the distant reaches of the universe. With an unprecedented combination of breadth and depth, it will open a new era in observing and understanding our universe. It is one of the most complex and sophisticated scientific instruments ever built. It is orbiting our Sun 1 million kilometers out in space in temperatures of -266 degrees Celsius. It is a time machine that will peer deep into the past and reveal unexplored reaches. And it will be our key to understanding where we fit in this enormous universe. Launched aboard an Ariane 5 rocket, the James Webb telescope has successfully reached its destination, unfurled, and begun its great adventure.
Hubble revolutionized astronomy. Hubble showed us the early universe. Hubble showed us what the universe works like. And as these revolutionary findings came along, people realized we need a next generation space telescope. This was 25 years ago, and this is how Webb came into being. Now, you can see 25 years of development time. This is not unusual for a large space mission, from the first idea to fruition, to the launch. And this is why these missions are really once-in-a-generation launches. We are witnessing something particularly special that an astronomer typically gets to witness once, if they are lucky, twice in their entire career.
James Webb Space Telescope is a collaboration between NASA, ESA and the Canadian Space Agency. So altogether that's 24 countries, lots of industrial companies academic institutions, universities, and thousands of scientists across the whole world are now waiting to use the telescope. So by combining the power of the best in engineering and science from all of those countries in this international collaboration, we can do much more together than we could do on our own.
The origin of Webb is the search for our origins. We want to find out where the first galaxies formed, how they formed, when they started making their stars in the very early universe not long after the Big Bang. And to do this, Webb uses its big mirror and its infrared vision to look into these really early days, observe the light from these galaxies that's been traveling to us for billions of years, and it shows us these galaxies, how they were billions of years ago.
Sure, so infrared is a longer wavelength than visible light. So we can't see infrared, but James Webb can. And what's important about an infrared telescope is it allows us to see through clouds of gas and dust and see the planets and stars and galaxies that are beyond. In addition, James Webb has a larger mirror than Hubble, so it can see back further in time, and it's orbiting at a different point.
James Webb is very complementary to everything that has been done before, to Hubble, to Herschel, but will be a huge step forward just because the collective area is huge. 6.5 meter is pretty impressive. Hubble, as a comparison, was 2.4. So we're talking of a collective area which is much bigger, much more sensitivity. We say 100 times more sensitive. With a complement of state-of-the-art instruments which will take images and spectra in wavelength regimes that we haven't explored as much from space up to now.
The telescope houses 4 scientific packages: MIRI, a mid-infrared instrument; the near-infrared NIRCam, NIRSpec, a spectrographic analyzer; and the NIRIS imager and guidance sensor.
The near-infrared spectrograph, or NIRSpec, it's one of the 4 scientific instruments that we fly on James Webb Space Telescope, or Webb Telescope. It's very important because it will allow us to analyze the light of the astronomical objects we will observe. A spectrograph works very much like a prism. In fact, there's a prism inside our instrument and other gratings, and they, like the prism, splits the white light into its rainbow colors. These instruments will split the near-infrared lights from the astronomical object into its components. And this is very useful to scientists because from that they can understand the physics of the objects they are observing, what are the temperature, the elements, the physical condition, and therefore we can understand what's going on the objects we observe. So we will observe all sorts of astronomical objects, from galaxies, and the focus is very much on very far away galaxies that are 13 billion light years away from us, so back in the far past, that they were forming soon after the Big Bang, from very what we call nearby objects, which are not really nearby, but they are exoplanets in stars around our neighborhood, the neighborhood of the solar systems in our galaxy. So this is the type of objects we will observe, and investigations. It's about understanding what are the atmospheric condition on the exoplanets, or what are the physical condition of the galaxies we observe far away. So, going back to the very far away galaxies, this instrument NIRSpec will play a crucial role in observing this far away galaxy and telling us what's the physics. So again, what are elements are present, in which proportion, what are the temperature, and that is fundamental if you want to understand how galaxies form, which is one of the big questions we have in astronomy. We see trillions of galaxies around us, how all these galaxies formed, and with this instrument we can piece together more of the puzzle. it complements the other instrument because of its function of a spectrograph. So on the Webb telescope, we have cameras, other type of spectrograph, one particular MIRI, which is also a partially European instrument, which will focus on the mid-infrared light. Near-infrared is the focus of NIRSPEC. Analyzing the light that comes from astronomical objects in the near-infrared wavelength range. While with the camera we see images, so we detect the objects and we know where they are and what are the main characteristics. With NIRSPEC we focus really on certain objects and analyze the lights and split the lines into its components, and with that understand the physics of the objects we are observing.
The telescope is in a halo orbit at the L2 or second Lagrange point and is orientated away from our Sun, with the sun shield keeping the instruments at their very low operating temperatures.
Where is the telescope pointing relative to the spacecraft? So we waited for the near-infrared camera to get the detectors cold enough so that we could take images, and we did some evaluation of that. And once we were convinced that it could take images, we were really trying to determine if we pointed at a bright isolated star, where's the telescope pointing? So we picked a star that was very bright and didn't have any stars near it that would contaminate the image. We know that the primary mirror segments aren't aligned yet, so they actually act like 18 separate telescopes, and we expect to see 18 separate images, one for each mirror, that are a little bit blurry at this point because we haven't aligned or focused anything. And so we pointed at a bright star and we made a mosaic. We actually took the near-infrared camera and we took images in different parts of the sky, and then we looked for the 18 spots from the 18 different telescopes, if you will, and we were very excited to find them. They were actually very close to where we were pointing, well within our expected size of where they might land. And the 18 spots were actually fairly close to each other as well. So really everything was very close to what was predicted and much better than what we considered to be the worst case pointing. So we were really excited about that.
Over the following months, each individual mirror was adjusted and focused, then aligned together to create one single image. The alignment image of the single bright star gave an indication of the power of the Webb telescope. As seen here, behind the bright star, the image captured numerous distant galaxies. The science team then captured several sample images of different objects.
The first images from the James Webb Space Telescope are designed to demonstrate the full range of the capabilities of the telescope.
Scientists then sat down and studied these many test images, which amazed the team.
The cluster is, it's probably bigger than that. There's lots of light. Yeah. But I think when you stretch the background, we didn't dare to say. You should have said it. Yeah. This is Iraq moving from the 70s to the 80s and 90s. Even in your camera, it really stays the same in all wavelengths.
We're seeing a sample of the amazing science that Webb will be able to do over the coming years. Remember, it's just a sample. So we are seeing scenes and vistas from across the universe, toward the first galaxies, to stellar birth and stellar death. And we're seeing an exoplanet spectrum for the first time with Webb, showing water or steam in its atmosphere. So here, what we're seeing in this deep field image, Webb's first deep field, is a massive cluster of galaxies. And what this cluster does is it bends the light from even more distant galaxies coming behind it. And you can see that as sort of bananas or streaks in the field. And this field allows us to look for some of the very first luminous structures in the universe, the first stars and galaxies. And this was one of the reasons that Webb was originally built. So with the Southern Ring Nebula, the image here, what you see is a star that is similar to our own sun, but 5 billion years in the future when it dies. And so when stars like that die, they push off the outer atmospheres, and this gas cloud you see is filled with elements like carbon and oxygen, kind of elements that we are made of. And this is how dying stars seed the galaxy with these elements that ultimately are important for the formation of life. So here we are seeing a small group of galaxies that what we call interact, actually colliding with each other. And this is a very fundamental part in the evolution of galaxies. They bump into each other all the time. And when they bump into each other, they create shock waves. And in these shock waves, you have this tremendous formation of new stars. And you see these shock waves in this image here, and you see the formation of stars there.
Yes, this is a set of galaxies that are sort of locked in a cosmic dance, and so they're moving, and they're, two of them are merging, and we can see all of them moving around in that, and their interactions.
You also see the galaxies superimposed on this field of distant galaxies in the background, whose light has probably traveled through the universe for billions of years. And so this is very typical for Webb images, that everywhere we look, we're going to have these distant galaxies in the background.
And one of the main things that we want to look at with the James Webb Space Telescope is the most distant galaxies in our universe, the furthest objects away. And that also means that they were the first objects to form after the Big Bang, the first stars and galaxies about 13.5 billion years ago. The reason that all of their light is now in the infrared is because the universe is expanding. And as it expands, the light from those most distant objects gets redshifted to infrared wavelengths. So again, Hubble can't see them, but the James Webb Space Telescope is designed exactly to see these very distant, very faint objects.
Those emission lines, yeah.
Oh yeah, this is such a beautiful image, and maybe my favorite. What we see here is a stellar nursery, a cloud of gas and dust that is actively forming new stars. And you see this as sort of a landscape that looks like mountains because the cloud is being eroded away by hot stars that's off the field to the top. And they're cooking off the cloud, and as they do that, they push on it. And so what that means is that you can form new stars sort of close to the surface of the cloud there, and you can see those stars popping out, and you can see them also create jets and outflows as part of this process that move through the cloud and create these streaky structures in it.
In comparison, the Hubble imagery here captures the visible light. Now, compared to the Webb images, you can see the dark dust turn transparent, revealing what is within and behind the veil.
I'm really excited about James Webb and the spectroscopic capabilities. It's absolutely revolutionary, the sensitivity and the resolution we can get to look at the dust and the forming stars in some of the very most distant galaxies to us, where we can actually see individual stars and work out what the chemical compositions they're producing in terms of dust and the minerals they're producing and the life cycle of matter in the universe, that chemical evolution of galaxies. And no other instrument, no ground-based instrument can do this because of the atmosphere. Only space-based instruments can do this. And previously, the previous generations have been so small they've been able to only look at galaxies in the Milky Way or in the Magellanic Clouds. But James Webb will be able to push that envelope out to lots of galaxies in the local group, and so we can look at very different formation scenarios towards the early universe. So that's what I'm most excited about, is these dying stars and forming stars.
The hope is Webb will be able to see so far back in time, it will reveal the very first galaxies and stars created after the Big Bang.
Lots of big questions. How do galaxies evolve? So the Hubble Deep Field has given us some hints of what we think is happening, but we haven't been able to see it in enough detail or with enough galaxies to really know. So it's going to fill in, almost you could think of it as a gap in time between the Big Bang and the galaxies we can study with Hubble, and we'll find galaxies that are in that gap.
This image is of the spiral galaxy IC 5332, which is over 29 million light-years away. The infrared web sees through like an X-ray into the interior structure of the galaxy.
Well, it's going to allow us to understand every phase of cosmic history for the last 13.5 billion years. So we'll be able to answer questions like, how are galaxies formed and where do we fit into the cosmos? We'll be able to see the formation of stars and planets. We'll also be able to understand atmospheres of exoplanets.
The James Webb also captured images of local residents in our own solar system. Here is Jupiter seen in the near-infrared. It reveals the polar auroras and the heat signatures deep within the clouds of our largest neighbour. Here is Neptune as never seen before, its rings clearly visible along with several of its moons. The most prominent features of Neptune's atmosphere in this image are a series of bright patches in the planet's southern hemisphere that represent high-altitude methane ice clouds. More subtly, a thin line of brightness circling the planet's equator could be a visual signature of global atmospheric circulation that powers Neptune's winds and storms.
I think the great thing about Webb is that it actually touches all of astronomy. So because it's so flexible, you can use it to study things inside our own solar system, but you can also use it to find examples of the very first galaxies. So it really is spanning almost the entire history of the universe. So it's really going to be transformative to lots of different areas. I think the two areas that are going to be transformed the most are my own field, which is finding and understanding these very early galaxies, and then on the other end of the scale, actually looking at planets around other stars that are relatively nearby to us. But I think every single astronomer in the world will ultimately be taking some of the results from Webb and incorporating it into their own research.
Astronomers have made giant steps in our understanding of the universe over the past decades, but there remains much to learn about our cosmic origins, and the range of questions waiting to be answered is causing high expectations.
Webb is more than tens of thousands of scientists. Webb is 8 billion people looking for the origins.
Orbit, a unique perspective on the planet. The permanently manned International Space Station circles overhead. It too gives us a unique perspective on science, health, and industry. The benefits of manufacturing in zero-G is spurring other countries and private companies to join this elite club of manned space stations. Low-cost, reusable manned spacecraft is the key to industrial expansion into space. SpaceX, with its Dragon spacecraft and Falcon rocket combination, is fulfilling that need. And other companies will follow.
It will become possible for people, I mean, of course, when I see all this, I've just yesterday seen the Dragon capsule right in front of me. We were able to get closer up to the same level. And I have to say, this is so fascinating. I really would like to step in and sit down and take off. It is a dream for many people.
Currently, the ISS is the only destination. The station is 23 years old and is reaching the limits of its ability to service other industrial needs. However, it is imperative to keep the research and science going.
Because we do so much work on the space station, research, experiments that really help humanity, but also give us a different view of our planet. And at the end, we want to protect our planet, and our astronauts are really giving us messages back, which is quite unique and quite nice.
When we look at the science that's done on the space station, it's benefited us on Earth in a lot of different ways. And I think one is a very basic way, and that it's given the opportunity to scientists throughout the world to think about science in a different way. When we think about life as we know it, one fundamental property of all life has been gravity. And one of the first things scientists do is they think, what happens if we take gravity away? And on the International Space Station, we're allowed to do experiments that study just that for long periods of time. So we can study the effect of gravity on things, on people, and then sometimes we can combine that with the effects of radiation. We can also look at, when we think about future space missions, we know that it's going to take a while to get to Mars, and it's going to take some time to get farther. So the International Space Station has given us an opportunity to see what happens when humans are in a space environment or in a microgravity environment where they're in free fall for long periods of time. And this is really important, so we understand the effect of the lack of gravity on humans. We also understand what it's like to be confined in a small environment for long periods of time. And we're starting to understand just the kind of technology we need in order to create safe travel for humans and also to address some of the challenges in robotic missions far from Earth.
The most recent addition to the ISS, a Russian segment with a European robotic arm, will help alleviate the stretched resources and capabilities of the station.
The ERA arm is completely symmetrical. This means it has a hand or an end effector at both sides, and that each side can serve as the tip as well as the shoulder. So it means that if you have multiple base points on the Russian segment, you can go from one base point to the other, then release your tip or your shoulder, which becomes tip, and then manipulate a payload. So in that sense, it has freedom of motion on the space station.
The robotic arm can be used for example, take payloads out of an airlock autonomously without the risk of an extravehicular activity, for example, and put equipment on the outside. It can be used for inspection. It can be used for putting big new modules, for example, and putting it on the space station, move big things around. And also it can be used to help the cosmonauts when they're doing a spacewalk, to move cosmonauts around or big payloads while the astronauts and cosmonauts have their hands free to work on the outside. So it can be used in several ways.
When we operate the ERA on the ISS, we're obviously going to learn a lot about how to use robots in space. How the robots work in space. We'll have feedback to our engineering process if we finally know what is the performance during its use in space. But we'll also learn on what we can best do with robots, what we can best do with people, and learn about the cooperation. And all of that is going to be very, very useful when we would go further into the universe and still have for sure robots initially, but maybe at some point in time also people with robots. So we're really looking forward to all what we can learn from the experience on the ISS with ERA.
Another addition to the station, delivered by a SpaceX cargo module, is a commercially funded Bishop airlock module. Operated by robotic arms, the commercial airlock allows easy transfer of payloads from within the station to outside for external deployment and to launch CubeSats, which is a burgeoning operational requirement. This will allow for more commercial payload throughput for industrial applications.
one issue that some European scientists worked on is that, first of all, we know that astronauts, after they've been in space for a long time, it's like their sense of taste changes a bit. And the longer they're up there, the more they crave spicier foods or saltier foods. So they start adding more salt to their meals. Well, one of the things that happens as they increase their salt ingestion is that it changes the pH of their blood. It makes it a little bit more acid. Not a lot, but just a little bit. And so the body adapts to this acidity by trying to raise the pH just a little bit by providing calcium that comes from our bones. So they actually have increased dissolving of the bones to get that calcium to bring that pH up. But at the same time, we're also seeing that because they don't use their bones very much, because in a microgravity environment, you don't have to fight gravity to stand up straight, that they're already experiencing some bone loss. So we're starting to see that because of this, we're starting to see that this change of taste results in an increase in salt consumption that can actually speed the bone loss in space. So here we're seeing two different effects, and we know here on Earth, we now know that perhaps the increased salt consumption isn't just a cardiovascular effect, but it could have perhaps contribute to bone loss and osteoporosis in humans here on Earth. And we didn't really see that effect until we went to space. The International Space Station provides a platform that we have humans that can act as subjects, but also operators of science. And it's also the only platform that we've had where scientists have the opportunity to do an experiment, see the results, and come back and prepare another experiment. And if something doesn't work, or if they have a second opportunity. And unfortunately, we don't see that with other missions.
What is next? We have now just a bit more than 20 years of ISS operation, very successful, and really incredible science and experiments that have been conducted, and we still learn every single day new things there, and this is really good. So what's next? What will happen is, for sure, that by the end of this decade, we will have commercial space stations up there. There are about 4 projects in the planning today in the US. And the question is, does Europe participate there? Does Europe have its own independent solution? And this is a big question that we need to address. But yes, the space station as we know it today, at the end of this decade, will not exist anymore and will be replaced by some commercial stations. And this is a big change. And Europe needs to be active and show leadership in making this change and really be part of it in this next era, which will come at the end of this decade.
2 commercial projects are well underway to develop commercial stations for industry and tourism. Axiom Space are developing their station to be assembled in 4 modules whilst attached to the ISS. The 4th module will allow the station to deploy its own solar panels and become independent from the ISS. Eventually, Axiom Station will detach and orbit independently from the ISS.
Hi, I'm Gerard Valle, and I'm the Structures, Mechanisms, and Soft Good Lead for Sierra Space Life Habitat. We're really just testing the structural restraint layer, which is what carries the load, and it's 1/3 the size of a life habitat.
So the restraint layer is made up of a material called Vectran. Vectran is an extremely high-strength material, performs really well in this application. It gets us the best performance while maximizing the livable volume inside the habitat.
Pretty amazing.
Sierra Space has been successful in developing their inflatable modules and are also developing their own spacecraft, the Dream Chaser, to service the station called Orbital Reef. First developed in test flight as a crewed reusable space plane in 2013, the Dream Chaser was not selected by NASA in their commercial crew program. However, Sierra Space persisted with an unmanned cargo version and have built 3 so far. The design of the lifting body was derived from an earlier cancelled NASA project, HL-20 spaceplane, a concept from earlier lifting body designs like the X-24 and HL-10. To be launched conventionally on a Vulcan Centaur or Ariane space rocket and to fly back to Earth and land on a runway like the Space Shuttle. The craft will be powered with a vortex engine burning propane and nitrous oxide. It will be able to carry 5,000 kilograms of payload to the orbital reef, and eventually a crewed version will be capable of delivering between 3 to 7 crew or paying tourists. One growing problem, yet to be resolved for these new stations and other orbital assets, is space debris.
At the moment, the most known encounters are between active satellites and space debris. An example of such an event happened in 2009, where we had a collision between an active telecommunications satellite, Iridium, with an inactive space debris satellite, Cosmos. So this collision actually resulted in thousands of fragments, and many of them are still in orbit.
The danger of space junk destroying operational satellites and even manned spacecraft is a growing concern.
Space debris is the result of our activities in space. So we have
no longer functioning satellites, and we have spent upper stages and the fragments. And in total, we know of about 28,000 objects that we can track, that means follow up from ground. We know of 900,000 objects that are larger than a centimeter. And we know of about 128 million of objects larger than a millimeter. And that shows that the largest contribution in numbers are these small fragments. And unfortunately, collisions and explosions are forecast to continue in space, and that means the population will still grow.
We are launching more and more. In the past, it was only the big space nations, let me call it their way, that were launching. By now, space has been opened up to commercial activities, and therefore we see more and more satellites being launched. Is this an issue for space debris? I would like to say no, if people behave properly. So if we really manage in a proper way the end of life of the satellite, it's not going to be an issue. The point is, will we manage those satellites in a proper way, yes or no? And we see that there is a tendency still to disregard what do I do with my satellite once it reaches end of life, and not consider it since the very beginning. Situation has improved a lot in the past 10 years, but we still have to do some teaching on how important it is to be considered since the very beginning of the design of a project.
Several concepts are in play to remove this orbital debris. For the larger objects, capturing them with spacecraft with arms or grapples, then performing a deorbit burn, dragging the debris down to burn up in the atmosphere. There is another resource available in orbit: sunlight. Why not capture it with solar sails and beam the electricity down to Earth? Massive solar farms comprising of many small mass-produced solar satellites launched into orbit on low-cost reusable rockets. Assembled together in orbit using advanced robotic techniques, and once completed, these satellites will collect the full power of the sun's energy 24 hours a day, 7 days a week, and beam it wirelessly down to Earth to receiver stations, which will turn it back into electricity and deliver it to the grid. Space-based solar power, continuously available, inexhaustible, and sustainable. A scalable energy source that could help meet the world's clean energy goals. Sea level rise is one of the most serious consequences of the human-induced climate crisis. The water rise is from heat expansion of the oceans, melting polar caps, vanishing glaciers, and the loss of fresh water. Satellites are an essential tool to monitor the changes and help climate modelers prepare us for the future. NOAA GOES-T satellite in geosynchronous orbit is a recent addition of the next generation of satellites. It is the Western Hemisphere's most sophisticated weather observing and environmental monitoring system, covering over half the globe. Along with the decades-long Sentinel series of satellites. Sentinel-6, a collaboration of European and US space agencies and climate monitoring institutes, is continuing the mission of uninterrupted, sophisticated data gathering for climate scientists and modelers.
Well, the main instruments on board include a dual-frequency radar altimeter. And this is the primary instrument of the mission, and that's the one that's measuring sea surface height, significant wave height, and wind speed over the ocean. And from those measurements, we can actually have the superb measurements that we expect of sea level rise, but also the waves. The significant wave height, which is the top 1/3 of the waves, if you were to look at them in time. So the biggest waves that you would see. This is important for marine operations, and the altimeters provide perhaps some of the best data sets that we have today over the global ocean. We have plenty of buoys in the ocean that measure waves, but they're often in the coastal zone, and it's only when you go to the altimetry that you can really have this global coverage.
We all know sea level is rising. And how do we know that? Because we measured this since the 90s from space through a series of satellites. It started with Topex Poseidon, which was a French-American satellite, followed by the JASON 1, 2, and 3 series, which was also a French-American satellite. And Sentinel-6, as you said, also called JASON CS, stands for Continuity of Service, is meant to go in orbit to follow JASON 3 to continue the record of the sea level since about 30 years. And we want to continue that record for another 5 years and demonstrate and quantify the sea level rise we have been observing since the 90s. In average, about 3.2 millimeters per year, even though the scientists tells us in the last year this has been accelerating, in particular due to the acceleration in melting of ice. So over the last years, it's above 4 millimeters every year we record in the sea level.
We talk about the impact of melting snow and ice surfaces in terms of what's known as the albedo effect. When snow is dry, it's very reflective, and of course that helps to reflect sunlight back out into space, and the consequence is we can reduce the amount of melting this way. However, as ice and snow melt, the albedo and the reflectivity becomes lower, and this has the effect of absorbing more of the solar energy. This contributes to further warming and further melting. And so it's a runaway progressive effect caused by the reduction in the albedo.
Satellites are a major source of global, timely
long-term data sets, which is in particular very important for climate, because we need to have long-term data series to actually understand how the climate is changing over decades, for example, and to also understand what the trend of these changes are going to be. So we are using a large variety of different data sets. We're mainly concentrating on the European Space Agency's data sets, and there's a mixture between data sets that come from, a heritage mission, like, for instance, Envisat and ERS, because we're looking also back, of course, in terms of climate, but we're also using data that are coming in right now, for example, from the Sentinels missions that are running under the Copernicus program that we are running together or collaborating with the European Union and EUMETSAT together. But we're also using actually quite new technology and satellites that address scientific questions that haven't been addressed before. So it's a mixture of different data sources that we are trying to combine in these climate data records.
What we do is we also work with partner agencies worldwide. So we exchange data over climate. We do work on calibration activities. We support activities linked to, for example, ice loss volume monitoring, and we have done that with the US partners over INBE campaign over the Arctic region.
To calibrate the satellites in orbit, scientists on the ground take measurements in situ all around the globe, from the Antarctic to the Arctic and glaciers around the world. They then compare results and validate the satellite data.
And we're producing climate data records, so long-term data records of climate-relevant indicators, let's say. One of them you see behind me. We are also producing climate data records for glaciers, in particular the extent of the glacier, the velocity, but also the elevation.
The ice loss in the Alps is comparably strong. So we have similar strong mass loss, I think, in the Andes of Peru and Bolivia, but also in Patagonia. They have similar rates. But the most difficult thing or problematic thing is that this ice loss in the Alps is still increasing. So now I think for something like 30-35 years we see higher and higher loss. And this takes place despite the fact that the region where ice can melt, the so-called ablation region, is shrinking. And this is a very strong signal for accelerated climate change and an increased forcing, which means that temperatures have to increase and push the snow line higher and higher, so that more areas are exposed to melt.
Those projections tell us what glaciers will look like. What they will look like very much depends on what we, human beings, will do next in terms of greenhouse gas emissions. So if we manage to mitigate climate change very much, we will have glaciers that will still shrink, but will shrink a lot less than if we don't manage to get hold of this climate crisis that is literally unfolding. So in the worst case, where really our emissions will continue to go unabated until the end of the century, well, this place where we're standing is going to be ice-free for sure. But even the highest elevation that we see here, they'll most likely be ice-free as well. On the contrary, if we now really manage to put effort in abating emissions, we'll be able to save, say, at least 40% of the ice. So half of this place is gone anyway, but still there will be something that we can look at and that we can show to our children and that our children can show to our grandchildren.
I think the recent record since Cryosat, one of our satellites, has been flying, has shown that there's quite some fluctuation in the amount of ice transferred from land to the ocean. However, we have seen that sea level rise has been accelerating over the last several years. One of the reasons is thought to be related to the increased melting of land glaciers. And a recent publication has shown that, in fact, the contribution of glaciers to sea level rise is increasing. And we've gone from a situation in the 1970s and 80s where it was contributing only a fraction of a millimeter a year to something closer to 1 millimeter a year. This is around 20–25% of the sea level rise signal globally. And so glaciers are obviously having an increasing contribution to sea level rise over the last 2 decades.
The European Space Agency is doing a lot in providing the evidence for a changing climate. If you think about the Earth observation program, for example, I think the majority of activities are really directly addressing this question. And it starts at the perceiving new satellite measurements. So, one of the core activities of the European Space Agency in the Earth observation program is, of course, to build satellites. And there's different flavors of these satellites that address, new technologies, new scientific questions, like, for instance, the Earth Explorers. But then there is the Sentinel missions that we are developing in collaboration with the European Union and with EUMETSAT, who provide, for example, continuity on many of these measurements, but also improve over coming decades, because we have a lot of experience in these measurements. And I think so we're doing in ESA, I think something, it's almost like covering the entire food chain of providing climate relevant information. And I think this is quite an amazing fact, because we really follow through from the beginning of the measurement up to the point where we're actually talking to the people who put the policies in place. And I think that's a really good foundation that we're providing from the ESA's perspective.
So when you fly around the Earth at 400 kilometers, you have a very unique point of view that is at the same time a privilege and a curse. It is a privilege because, of course, not many people get to do it. Not many people get to fly in space and look down at the Earth. It is a curse because what you see is, at the same time, so beautiful and so fragile that it certainly breaks your heart. And it is what inspired me to start talking about what happened, what is happening on planet Earth, and about everything that we take for granted today. And as a matter of fact, that same feeling of helplessness and desire to do something, I felt in these last couple of days, talking to the scientists, talking to the explorers, and being myself part of the group on this glacier and looking with my eyes, touching with my hands, the same things that I felt from space. So if I had to summarize the feelings, which is always hard because feelings don't come in a linear way, they're always very mixed up. I feel a little bit of urgency. And because it's me, I also feel hope that people will listen and understand the urgency of what is happening and how fast we have to react before everything that we have will disappear.
Low-lying regions of the world, of course, are going to suffer the most from this kind of impact in terms of ice melt and sea level rise. Of course, countries like Bangladesh already suffering from the increased probability of storm surges as sea level rises. And coastal inundation is a problem for millions of people in Bangladesh. We also see it in more developed countries. We have a situation in Venice during seasons of the year where tidal range and storm surges combine with sea level rise to cause what's known as acqua alta. And there, the whole of the city of Venice is inundated by water on a regular basis during these periods of time. So I think the societal impact of coastal inundation and flooding can affect millions of people in the future. And so we need to monitor the effects of melting ice and sea level rise.
we got the long-term data, and we got the long-term trend, and we now finally realize that you have the long-term trend, but you also have superimposed local variations. So some years it stops, and other years it goes very quick. So it's a really very dynamic system, and that just really means that we have to have a continuous monitoring from space.
I believe that there is an awareness that is growing, but is not enough yet. So water being probably one of the resources that we really need to check, and we are here because of that. Water has a cycle that we have interfered with. Ice turns into water, turns into atmospheric water, and it accelerates hurricanes, it accelerates flooding, it's all connected, and we have interfered with that cycle. So now we have to do something to take a step back. Well, one of the things that we can do is preservation without pollution. So little steps that everybody can do. Have a bottle of water and reuse it instead of continuing buying extra new bottles of water and polluting the earth with the plastic and using extra water that we don't need. We can live on very little water. We are just not used to do it because we don't think about it, and we take it for granted. I believe that the perspective that I have comes from the awareness that on the space station we live on very limited resources. We have to recycle them, and we have to respect that awareness.
What we're doing in the Climate Office, and not just in the Climate Office, but in the European Space Agency Earth Observation Program at large, is, I think, 99% supporting the course of understanding what our climate is doing, how our climate is changing, and that in turn can actually inform policymakers to take action of what needs to be done to either mitigate that effect, so basically, for example, limit emissions, or to adapt to things that we cannot change anymore. It's a very important physical evidence to give decision makers and policymakers a base to come up with plans of how we address this issue.
Ice is changing a lot, and ice is melting a lot. Whether it's a problem, of course, long term it's a problem because the sea level rise will go up. But it's also to some degree an opportunity for some of the Arctic countries that they can develop their countries. So it's climate change, monitor what is happening, make sure we can give a qualified statement, and especially the space is very important to give a qualified statement of what is really happening and not just some model prediction or some fancy outlook which could be way off. So I think we're the guys who give the hardcore facts. And as you say, I've been here for many years. I've seen the change on my own eyes, because before we even got involved with the European Space Agency, we did a lot of airborne, a lot of mapping work. We mapped with the first satellites already in the very late 1970s as the very first users of satellite navigation, namely for mapping remote and distant areas. So it's been really amazing to see, and also amazing to see the changes, and the changes are big, no doubt about that.
And we're producing these data sets also for the benefit of addressing these international climate drivers, so that we actually know where we're standing at the moment in terms of the state of the climate and what actions need to be taken in the future in terms of policy and decision making and adaptation and mitigation actions, for example, in the future.
Because of the availability of information that we are constantly bombarded with, there is a general feeling that we can all be experts at everything and come up with our own opinion. I don't want to dismiss anybody's opinion, but I do want to listen to what experts and people who have devoted their lives to a certain study have to say. Now, it's a cycle. We have scientists who use their instruments to gather data, study those data, and come out with a theory. And once they come out with a theory and everybody agrees to it, then we should probably listen to that. But how do they get these instruments? How do they gather that data? Well, there is a whole community of people technicians, engineers, astronauts, operators that work constantly, incessantly to create the instruments and to position them and to create the basis so that the data can be collected in the correct way.
The sea level will go up, no doubt about that. So people in Holland and the very low-lying areas, they should have good reasons to be concerned. So do we in Denmark. But again, right now it's only 10 centimeters, so we are talking 2,100. We talk anywhere between 30, 40 centimeter and a meter. Then it's a little bit more concerning. And again, that's where this long-term space mission, they would tell these people who make the modeling and the prediction in the future, if they made the modeling earlier, will it really fit what we see today? If you take all the data today, will it fit in 10 years? That's why you have the big value of these continuous data. And also the continuous measurements really of, do the satellites measure the right thing? Is the radar really measuring the surface, or is it measuring somewhere else on the ice? That's all the questions we are concerned with.
Most scientists agree we are past the point of no return. Now the focus is on trying to mitigate the most serious effects on the planet.
So it is a concern, of course, and eventually we should do something about it. And again, the space mission can tell you in the long run, if you change something in the CO2 with the political side, will it really matter? And for instance, the CO2, also in the Copernicus program and the ESA missions, you have CO2 missions, which are really useful to actually pinpoint who are the bad guys in this game, who is not cutting back eventually.
As a scientist, I think we can provide data, and the satellite data help us to do so. The issue with the glaciers and the shrinking glaciers is a global scale phenomenon where people are really concerned that in the future there is no more ice or much less ice. And what we can provide as scientists is solid data about how much ice there is, how the ice masses change, and maybe when you do some computer modeling, also how much ice there will be in the future. And over the past 20, 30 years, I think the reporting from us was more and more, yes, they are shrinking, and glaciers are shrinking globally, and they do it stronger and stronger. And we can repeat this information again and again and have it in IPCC reports and say, hey, there's a problem. But of course, in the end, it depends if this message is picked up and converted to action. And here is then very soon the place where the engagement of scientists end, because this is a political thing, and what we can do is provide the best data and the best uncertainty information we can get and say, really, we are sure about this and about this and about this, and not so sure about this. And then politicians have to decide on if they want to do something about it. And we hope that at some point this will happen.